This, I'm just saying, call this matrix B. Now, why is B invertible? One of the things we know, one of the more important things we know about determinant is that the determinant of a product is the product of the determinants. So if I calculate the determinant of this equation, I get the determinant of y is equal to the determinant of x times the determinant of b. This is not equal to 0. This is not equal to 0. Why? Because we're assuming that they're fundamental solution matrices, right? Hence, the determinant of B is not equal to 0, which is tantamount to saying that B is an invertible matrix. And that's the theorem. So this is interesting. This means that any two fundamental solution matrices are related by a constant multiple of some given invertible matrix. All right? And at first glance, you might be like, okay, well, who cares? Well, this actually gives us a way to calculate things that might be surprising to you. So we'll come back to this in just a second. All right? Assuming I have time. I think I've got time. Not sure we're going to make it today. Not sure we're going to make it. We're going to try, though. So I need to define for you guys, well, a corollary to that theorem I probably should work out before I do anything else. Right? How is that, can you tell me how that constant matrix relates to everything else going on here? Can you tell me what that constant matrix is in terms of the X matrix and the Y matrix? Notice X and Y are matrices of functions in that context, right? So like, look at this. We have this like general identity, right? X at time t, I forgot what I wrote. Oh, Y at time t. It doesn't matter which one's X and Y really. But think about this, guys. This formula here, right? Did I get it right, at least? I'm trying to be consistent. We good? What times do these hold for? Well, this is true for all t in the reals, because we're dealing with the constant coefficient problem. So our domain, our solution sets have domains which are the whole reals, all right? Nothing so snazzy as like the series solutions where we had interesting stuff going on back there. So, I don't know, plug whatever time you like. Time 0, time t naught, right? If I look at time t naught, y of time t naught is equal to b times x of time t naught, right? So therefore b, apparently, is equal to y of t naught times x of t naught inverse. Thus, y of t can be written as y of t naught times parentheses x of t naught inverse times x of t. That actually gives you a specific prescription on how to calculate the matrix which relates the two fundamental solution sets. I have never used this formula. So you might be like, why are you telling me it then? Well, give me a second here. The most important fundamental solution matrix the most famous one, the most awesome one, is the matrix exponential. Matrix exponential is defined as such. E to the ta is I plus ta plus 1/2 t squared a squared plus 1/3 factorial t cubed a cubed. And I think that's enough for us for now. I don't know if you guys recognize this or not. I mean, this is the definition. You might recognize that as the Maclaurin series for the exponential, right? The Maclaurin series for the exponential, where I'm just substituting the matrix times time into the variable. This defines the matrix exponential. It turns out you can prove, I do prove in my advanced calculus class that that converges for any matrix. So the matrix exponential, it's a series of, it's an infinite series of matrices, right? So there's something to think about there. Why does that converge? It does, though. And better than that, it converges in an absolute sense. What that means then is that you're able to do term-by-term calculus on it. We can differentiate an infinite series of matrices term by term. How does that go? What's a ddt of e to the ta? We differentiate this, right? So we've got like ddt of ta, right, plus ddt of 1/2 t squared. You can pull the a out, it's constant, right? Ddt of t cubed over 3 factorial. Pull the a out, it's constant, you know? So what you got? You got an a, looks like a t times a squared. That simplifies to 1 over 2, t squared times a cubed. If we kept the next term, we would have had 1 over 3 factorial t cubed times a to the 4th, and so forth, all right? What are we looking at here? This is a times what? Factor out an I for that one, plus ta 1/2 t squared a squared, 1 over 3 factorial t cubed a cubed. Hey, what is that? I know it's been a minute since we defined it. I mean, like literally a minute. But there it is. That is e to the ta. Oh. What does this mean? Theorem. E to the ta is a solution matrix. Of dr dt equals to ar, right? It solves the necessary equation, right? You see that? d dt of e to the ta is equal to a times e to the ta. It turns out that the determinant of the exponential of e to the ta is actually equal to the ordinary exponential of the trace of a. And as such, this is not equal to 0. So therefore, you know, e to the ta is a fundamental solution matrix. This thing I just wrote down is by no means obvious, all right? And there's an easier way to prove this. What do you think the inverse of e to the ta is, though? Care to guess? E to the negative ta would be correct. Now, I don't have quite enough time to flesh that all out, but that is in fact true. And if I had another 5 minutes to talk about it carefully, I'd do that, all right? But what I wanted to show you is that we can apply this boxed equation up here to the matrix exponential, right? So if I let y equal to e to the ta, right? Y of t be e to the ta. And I let t naught equals to 0. Notice that y of 0 is e to the 0, e to the t times the 0 matrix, which is what? It is, well, not 1, but the identity matrix. See that series, it just becomes the first thing if we plug in times 0. So e to the matrix exponential 0, e to the 0 matrix is the identity matrix. And as such, this tells me that e to the TA is equal to, see what's happening here? When I plug times 0, t sub not equal to 0, this just becomes the identity matrix, so we don't even need this. And this over here just becomes x of 0 inverted times x of t. So this right here, guys, gives us a kind of sneaky way to calculate the matrix exponential if we already know a fundamental solution matrix. In your homework, I ask you to calculate the matrix exponential just after I've asked you to solve a system, one of the problems. You can use that formula to answer the question. It's a 2 by 2 problem, so the inverse of a 2 by 2 matrix, there's a known formula, all right? So, like for instance here, if we were just, you know, so we could look at x of t equal to, you know, we'd end up with like a 0 cos t sine t if we were to look at a equals to 0 minus 1, 1, 0, right? This is example 4. If you look at my second example, we can extract that for the 2 by 2 matrix that I just wrote. See that? Like that would be a fundamental solution matrix. See what I'm doing? I'm just ripping off the red part of the solution. I'd have this and that as solutions to dr dt over a. And then in this case, e to the ta, it would be equal to x of 0 inverse times x of t, which in this context would be the inverse of 0. Whoa, dude, no. I've only taken half of the, I only got half the story. What's the other half? Come on, guys. You're like, it's your example. It's not my problem. Fair enough. I'm missing a, ew. Oh, man. I thought it was prettier. Oh, phooey. I guess it's cosine t plus sine t, and this one over. All right, well, it was an otherwise good lecture. Anyway, I was trying to give you an example of my last formula, but we don't have what we need in front of us to like make the example easy, so I don't have 5 minutes to work out another one.